All right, classwork is on the chalkboard. We've got a distance time function describing the motion of an object. I want you to find the distance that the object has traveled after 5 seconds have elapsed. Then I want you to find the velocity of the object at exactly the 2-second mark and exactly the 4-second mark. And then finally, at the 3-second mark, find the acceleration of the object. Take just a few minutes to work these problems. Pause the video while you work, and then when you're finished, go ahead and resume. All right, let's go and take a look at these together. The distance after 5 seconds, really all we got to do, Jamie, is find...
just plug it in.
Yeah, plug it in, so d of 5, right? Just find d of 5. Plug it into the function. And the decimal's a little annoying. We know 5 cubed, of course, is...
125.
125, so 0.2 times 125 ends up giving us a 25. And then the 5 squared is
25
times negative 3,
negative 75.
negative 75. And then 5 times 0.5, 2.5, and so we get a very much negative answer here. After 5 seconds have elapsed, this object is actually way behind whatever the starting position was set to be, Jamie.
Negative 47.5 meters.
Negative 47.5 meters. So this is describing, it would seem, backward motion. Quentin, good to go on that. Then the velocity at both 2 seconds or 4 seconds. When we want velocity at a particular moment, we can't necessarily say, well, how far has it gone after 2 seconds? Divide that by 2 seconds. That would be average velocity. How far has it gone after 4 divided by 4? That's average velocity. We want the velocity at that moment, the active velocity, or we call it...
First derivative.
Well, we use the first derivative, but we call velocity at a particular moment the...
Or instantaneous.
Instantaneous velocity. I was trying hard not to use the word instant, right? The velocity at a particular instant, instantaneous velocity. And we do need, my next question was going to be the first derivative to find it. So we needed to find d prime of t, and what is that?
0.6 t squared minus 60 plus 0.5.
All right, I'm running myself out of room there. So at the 2 second mark, of course, that means we need to find d prime of 2. And let's see, square root of 4 times 0.6 is 2.4. 2 times the negative 6, negative 12, plus 0.5. And we end up getting here, Quentin?
Negative 9.1.
Negative 9.1. Which is moving backwards at 9 meters per second. That's approximately a sprinter speed. So this object is running away from something, backward from something, or moving at least at negative 9.1 meters per second. What about at 4? Well, again, same thing. Square at 16, that's 9.6, negative 24, and negative 1. And Jamie, here we end up getting, or positive 1, here we end up getting...
Negative 13.9 meters per second.
Negative 13.4. What'd you have, Quentin?
I had negative 20.3.
Hold on. I might have done something wrong. Let's try. It's 4 squared is 16 times 0.6 is 9.6 minus the 24 plus the 1, which would be, plus the 2. So...
why is it... Okay, why are we changing the 0.5 to the...
Oh, that's a constant 0.5. I'm sorry, my brain's filling in a T. Thank you. So, Jamie, you might be right. Okay. Backtrack. I'm so sorry. 10.1, negative 24. What did you say you had? Negative 13.9?
Yeah.
Good job, Jamie. Negative 13.9 meters per second. Still moving backward, but going faster than it was before backward, which tells us it is speeding up at this point. Speeding up going backwards, but it is speeding up. Now we need to find the acceleration at 3 seconds, or Jamie, we need to find the
second derivative?
Well, instantaneous acceleration, which uses the second derivative. And what is the second derivative, d double prime of t?
0.12 t negative 6.
Oh, careful, 2 times 0.6?
1, 2. Oh, is it 1.2?
1.2 t.
Negative 6.
Negative 6. And so d double prime of 3 ends up giving us...
negative 2.4.
Negative 2.4. And again, remember acceleration in meters per second squared. So it's speeding up in a backward direction, not necessarily decelerating, which is normally how we associate negative acceleration, but in this case the negative indicating the direction of movement, because clearly it is speeding up at that in-between point. Questions on this? Questions on this? All right. Now another application, of course, of these derivatives, this first derivative, second derivatives, was in graphing. And I said if we can get rough sketches at least of our graphs using derivatives, because derivatives can help us to find and analyze what we call critical points. Good, critical points. And a critical point, remember, is where a graph begins to change direction. It was going up and all of a sudden it starts going down. Or it's going down and all of a sudden it changes and starts going back up. So these change in direction points are very helpful. And a critical point exists anywhere the slope of the tangent line is zero. Anytime there's a change in direction, the tangent line's slope will go to zero. And since we said the slope of the tangent becomes zero, well, what is slope of the tangent? The first derivative, right? The first derivative is the slope of the tangent. Remember earlier we said, here's a function, find the slope of the tangent line at a particular point. Well, that was the first derivative. So if we want to know where the slope is zero, we need to set the first derivative equal to zero, remember from our last lesson. But then also we said that a critical point could be where it goes from positive down to negative, meaning it would be at the top of the curve, or it would be a maximum point. Or if it was going negative and then all of a sudden it goes positive slope, well then it would be a minimum point. It is also possible that the slope could go down at a minimum, up at a maximum, then back down again, maybe to a minimum, back up again. So really the minimum points or maximum points could be perceived as local minimums or local maximums, not necessarily the highest point of the entire curve or lowest point of the entire curve either. But to determine whether it's max or min, right, we need to see how the slope changes, right? If the slope was coming positively, goes zero and then goes negatively, that means it's trending toward a negative slope. Starting positive, less positive, less positive, less positive, less positive, less positive, zero, negative, negative, more negative, more negative, right? If it trends negatively, we know we have a maximum point. If it trends positively, we know we have a minimum point. To see how the slope changes, we would need to use the second derivative. Slope first derivative, a change in that slope would be a second derivative. And so the second derivative told us how these critical points changed. Now, of course, just setting the first derivative equal to zero allows us to find x values of the function, but that's not all of the point, right? How do we get the y value? Yeah, go back to f of x. The original function gives you those y values. Turn to page 323 in your textbooks. Let's practice with a few of these here. Page 323. I want to start with a really fun-looking one, number 6. Yeah, we got f of x is equal to x cubed thirds minus x halves squared, or x squared halves, excuse me, x cubed thirds minus x squared halves plus 2. I'm struggling today. I blame it on lack of sleep. Shall we go with that? Go with lack of sleep? All right, so if you hear something nutty, just ignore it. All right, here's my function. Let's see what it looks like. And to determine what it looks like, we need to find the first derivative so we can get our critical points. Right? So we'll find the first derivative, and that's actually not nearly as hard as the outsider might think. We know it's actually pretty easy, Jamie.
X squared minus 2x plus 2.
Ooh. You're right about the x squared because the 3 comes out, cancels with this 3, and it drops. The 2 comes out,
and then cancels with the 2.
and it drops.
X.
And then this constant,
Spheres.
because its power is x to the 0. So we find the first derivative, and then to find critical points, we take the first derivative and set it equal to 0. At this point, because we have a quadratic equation, we're going to want to factor it. Set equal to 0 right here, so we need to factor it. Well, how do I factor? Pull out an x. Leaves us with, in parentheses,
X minus 1.
and so what are the x values of my critical points?
0, 1.
0 and 1. So 2 critical points, x value 0 and x value 1. But that's not a point yet. So to get the full point, abscissa and ordinate, Jamie, we said we go back to
The
original function and we find what is f of 0. That's pretty easy, class. 2. And then not as easy, f of 1. I don't know what that was either. F of 1. Might want a calculator here. Obviously, this becomes a third. We know this becomes a negative half. Common denominators. I'm too lazy. What do we get here?
1, 5, 6.
1 and 5/6. Lovely. All right, so there's my 2 critical points, but I want to know more than just what are the critical points. I specifically want to know, are these points at the top or at the bottom of a curve? So to determine that, I need the second derivative. Well, what is the second derivative here, Quentin?
2x minus 1.
All right, and what we're going to do is we're going to take the x values of the critical points and plug them in here. So f double prime of 0 and f double prime of 1. Again, f double prime of 0 is easy. And f double prime of 1, 1. All right, so negative 1. At the 0, the slope trends negatively. That makes this a maximum point, or a local maximum. And then here it trends positively, which makes it a minimum point. And if we were to draw kind of a rough sketch here, 0, 2, of course, pretty easy to plot. And 1, 1 and 5/6. Pretty close together. But this is at the top of a curve, and this is at the bottom of a curve. So there's this little ripple between them, and then it goes up, little ripple, down. And there we go. And that's what our curve would look like. So not a pronounced, like we've seen other cubics that have really pronounced end looks. We did one of those yesterday. Not much of that at all, just a little ripple in there. Questions on this? Do we remember this process from yesterday? All right, I want you to do a couple on your own. Numbers 4 and number 10. They're on page 323. Page 323, number 4 and number 10. Once you're finished with those critical points, go and draw a quick sketch of what it should look like based on your analysis. All right, check your work on number 4. Should have had a first derivative of negative 6x positive 6. Set it equal to 0. Maybe an easier way to be would move this over and get 6 equals 6x, right? Why factor it? I mean, I thought about that after the fact. Why am I factoring? It's not a quadratic. It's stuck in, well, again, go back to nutty today. End up with x equals 1. And if you did factor, you could. The negative 6x, negative 1, negative 6 can equal 0. Of course, x equals 1, but yeah, anyway, whatever. So x is 1. There's the x value, the critical point. Go back, plug this in. F of 1, I got negative 2. So 1, negative 2, our critical point. Find the second derivative, which is always negative 6. It always trends the same way, and that's downward. Which means at 1, of course, it's going to trend downward. And so therefore, it's a maximum point. And there's our curve, a parabolic curve down there, mostly in the 4th quadrant. Questions? Is that what you had? All right, number 10 is a little more interesting. We're expecting how many critical points? 3, 1 less than what it has, right? 1 less critical point. So for a first power, linear, you don't expect any critical points, right? It's always going to be straight line. Second power, you're expecting a parabola, which would be 1 critical point. So I'm expecting 3 critical points here. We find that first derivative, Jamie.
5.
On number 10?
It was the x to the 5th one.
That was an x to the 5th? Oh, I was looking at number 8. That's why. Okay. I copied it wrong. People screaming at their computers, that's not number 10. He's a doofus. I told you. All right, so I am expecting 4 critical points. Yes, that's why you said 4. All right, lovely. Jamie.
5x to the 4th minus 40x.
All right, and then we're going to set that.
Equals 0.
And when I do, I'm going to factor out.
On the 5x.
And it leaves me with in parentheses.
X cubed minus 8.
And can I factor that further?
Yeah.
I actually can, but I don't want to. What I want to do is I just want to set both factors equal to 0. Let's say if 5x equals 0, class x equals 0. And if x cubed minus 8 equals 0, then that means that x cubed equals
2. Or
8. And then I take the cube roots. Remember, how many cube roots are there? 3. But 2 of them are complex, going back to chapter 9. you can't graph complex critical points. So I only care about the real value, and that is 2. So there are 4 critical points, but you understand 2 of them are complex critical points, which are not graphed. 2 actual critical points will be graphed here. That's the 0 and the 2 for our x values. Questions so far? All right, when you find the y values, go back to f of x, find f of 0, which is, of course, Quentin 2. And give Jamie the chance to show off, because she's got f of 2, which is, yeah, it's that.
Is it negative 46?
Negative 46. So. It's gonna be fun to graph here in a minute, right? But we'll wait for that. We now need to know minimum maximum. Now, I'll be honest, 2 negative 46 had better be a minimum. If that's a maximum, I won't be upset, okay? But how do we know minimax? We use the second derivative, because second derivative tells us how the slope is changing. What is our second derivative, Quentin?
20x cubed minus 40.
And so for f double prime of 0, class,
Negative 40.
negative 40, and for f double prime of 2, we get, oh goodness,
120.
yeah, 120. All right, so at 0, the slope trends very sharply negative, which means it is a maximum point. And as we hoped would be the case, very sharply trends positive, making it a minimum point. So we've got our point 0, 2, and I'm not actually going to tick off all 46 of them, but over 2 and down 46 would be somewhere in the neighborhood of this. From here, it goes down very sharply. From here, it comes up very sharply, and so we get is a very, very pronounced N. Very, very tall and very, very skinny. Questions on number 10? All right, I want you to do numbers 2 and 8 now. I think these will be a little less obnoxious than number 10 was. Numbers 2 and 8. On number 2, the first derivative is -1, right? And so we set that equal to 0, and what do we call that? A lie. Or a contradictory equation if you want to go back. But it's a lie. -1 doesn't equal 0. Now it doesn't mean the whole function is a lie, but it means critical points are a lie. It's fake news. There are no critical points, right? There was no laptop. Anyway, I had to go there. So if there's no critical points, that means the graph has to be
or
straight line. Oh yeah. You mean y equals -1x minus 4? So how would I graph this?
Straight line here. -4.
-4, y-intercept, with a slope of -1. There's my first derivative slope. Rise 1, run backward 1, and we just connect those dots with a straight line, and that's how we graph it. No critical points because it never changes direction. Were we gotten, or did we figure it out?
Gotten.
You were gotten?
didn't get graph.
You figured out there were no critical points at least. Okay. All right, questions on this? All right, number 8, a little bit more legitimate, has 3 critical points. Now, are all of them real, or are some of them complex or imaginary? We have yet to see, right? Last big one we had 4 critical points. Well, really we ended up with 2. Here, of course, we had none. Here, supposedly we're going to have 3. We find that first derivative, and this time it is the problem I wrote on the board. Quentin?
Raised cube minus 4.
And we set that equal to 0, and this time we do have to factor, because it isn't just a regular equation. It's higher power, so we factor out, Jamie,
4x.
4x, leave us with,
X squared minus 1.
and if we wanted to, we could factor this further.
X plus 1, x minus 1.
Or you could just set x squared minus 1 equal to 0, add the 1, take the square. We'd still get either way, positive 1 and negative 1, and of course from here we get
0.
a 0. So we end up with 0, positive, negative 1. There's 3 actual real critical points this time. None of them went imaginary on me, or complex, actually. 0, 1, and negative 1. And Quentin?
Plug in 0 in the
And then Jamie?
We're gonna get 3.
Yes. And quantum to -1.
3.
Likewise gives a 3 because they're all even powers, which is going to make both positive and -1 behave the same way. All right, 3 critical points. 3 times the graph has to change direction. Jamie?
The first one is gonna be maximum.
How do we know?
You plug into the second derivative.
So we're going to have to find a second derivative now, f double prime of x, Jamie.
12x squared minus 4.
12x squared minus 4. And you said the first one, when we plug into 0, is a -4, and therefore you said
It's maximum.
it's a maximum point. Now, again, since this is even, both positive and -1 will behave the same way. So I'm going to be lazy and do f of both positive and -1. Either way, class, we get 8. And so I get positive. So at both of those, the slope tends to go up, making them minimum points at the bottom of the curve. And so for our rough sketch, 0, 4, 1, 3, -1, 3. It's going to go up from these two, but down from that 1. So as opposed to just going up, there's a little downward motion in the middle here, upward from here. And so that somehow looks like an emoji or something. And we're going to go down and then up, down and then up, and we get a W again here for our rough sketch. How do we do on number 8?
Didn't get the graph, but
Did not get the graph, but got everything else? All right, questions? You can set your books aside then for just a couple of minutes as we round out the hour here. Give you a function of x, g of x is equal to -1/4 x to the 4th plus 2x squared plus 3. Looks like a smiley face or something. And we get an M.
Mm-hmm.
All right, questions on this? All right, your homework for this evening is to do page 323, numbers 1 through 9, the odd. Page 323, numbers 1 through 9, the odd. But we'll be taking a quiz in our next lesson over using derivatives in distance time functions to find instantaneous velocity and instantaneous acceleration, and of course, quick sketch graphs using critical points. All right, have a wonderful rest of your day, and you are dismissed.